He's an instructor at National Science Department of Radiology. John has a PhD in electrical engineering and communication and math science from SC University, and he currently is postdoctoral training with very well at the Martin Center, working on coding for cell MRI. So today we're going to talk about the position of evolution. Thank you very much.
All right, great. Thanks, man. Thanks, man. And thanks for the introduction. Thanks for organizing. Thanks also to Lorian for organizing. I'm really happy to be here. It's nice to see so many friends in the audience. So I'm really looking forward to today. So I guess we're doing a Google Hangout, which is, a first for me, although I have to say it looks like there's an error, loading the app. I mean, if you guys want to take a quick look, I mean, it looked like it was working for a second, but then it kind of died on us. Okay, cool, thanks for your help. Okay, great. So, by the way, I think, can we turn the lights down just a little bit? I mean, I think that some of the images might have poor context. I don't want you guys to fall asleep. Oh, is there, yeah, that's good, that's good. All right, that's good. Okay, great. So I thought I'd like to, talk to you guys today about some strategies for high-resolution fMRI. Now I'm happy to have sort of an informal presentation. So if you guys want to interrupt me at any point, please go ahead. I think I made the presentation a little bit short, so there should be plenty of time for questions. Okay. So with that, let's see if this works. Okay, great. So the theme of today's talk is going to be high-resolution 7T fMRI. So recent advances in MR technology, such as massively parallel coil arrays, commercial high-field systems, give us images with smaller boxes. Here's an example of some 0.75 millimeter isotropic single-shot EPI we can achieve at 7 Tesla. What's interesting is that when Larry first put the 7T in Charlestown, people said you're never going to get EPI to work. And what's funny is that with this new hardware, we're actually able to get better EPI images at 17 than at 15. You can appreciate the anatomical quality of these images, but what's amazing is that these are the images that we're using for our fMRI. Okay, so with such small voxels, the question becomes, is the accuracy of our measurement really limited by the voxel size or by what we call the sort of biological resolution, the coupling between the hemodynamic response and neuroactivity and the underlying neuroactivity that we're seeking to measure? And this is going to be, again, one of the questions that I want to address during this talk. So this kind of quick introduction, I just want to give you, okay, all right, it's interesting, okay. I'd like to give you a quick overall outline of what I'd like to talk to you about today. So first, I'm going to talk a little bit about resolution, distortion, and image acquisition, and ask the question, what dictates voxel size? Of course, if we want to do high resolution, we need to make sure that our images are accurate. Next, I'd like to talk a little bit about the biological limits and resolution. This will be mostly kind of a literature review, and I would like to ask the question, how fine scale is the hemodynamic regulation, the biological resolution that we're interested in? Next, I'd like to talk a little bit about surface-based analysis methods and ask the question, can an anatomically informed sampling method from our signal give us improved accuracy? And then finally, I'd like to wrap up with a kind of survey of some novel acquisition techniques that we've been developing in the lab. I thought you guys might be interested in. That's the question again, how can we combine data across different modalities, anatomical, functional, structural diffusion? Okay, so with that little overview, first, as I mentioned, I'm going to be mostly focusing on second test and high field fMRI. Now, the bolt sensitivity, as you guys know, increases with field strength. Across the board, SNR goes up as we go to higher field strengths. But what's nice about fMRI is that because the delta T to star changes also increase, we get a nice kick in contrast to noise ratio as well, which is exactly what we need for fMRI. So this is nice. We get actually a super linear increase in functional CNR as we increase field strength. So that's as long as we're thermal dominant. I'll say a little bit more about this later. This translates to a reduction in scan time. So for population studies, fewer subjects are required. Also, we can do single subject analysis, potentially single patient diagnostics, but also it enables us to have smaller voxels. We can spend this increased CNR to achieve smaller voxels, which means we can sample the cortex, which is nice. We can reduce partial volume effects, less noise contribution from surrounding CSF and white matter. Also, as we go to higher field strengths, there is some weighting towards smaller vessels. We will not have much potential to talk about today, but this is another kind of feature at going to high field strengths. Now, as many of you know, there's some distortions and artifacts potentially when we go to higher field strengths. The strategy that we use to mitigate, I like to think of as kind of hardware-enabled solutions to get around these distortions, such as fast, strong head gradients, and nowadays we actually have fast, strong body gradients, and of course high-end receive coil arrays. So these two technologies together enable us to achieve faster acquisitions, faster EPI readouts, which gives us less distortion and less blurring. We're essentially able to sort of outrun the distortions. Just to give you a quick kind of sense for how we apply this in in Bay 5. So here's an example. This is just 2 millimeter isotropic single-shot EPI. You can see the sort of classic macroscopic susceptibility gradient distortions around the frontal sinuses and ear canals wherever we see tissue-air interfaces. So this is sort of classic, what we expect to see at 7 Tesla. With a little bit of acceleration here, if accelerated by a factor of 2, you actually see a lot of that distortion is mitigated. That's because we effectively reduce the echo spacing and therefore reduce the amount of distortion in the EPI in the phase encoding direction. We can push this a little bit further, go 3, 4, 5. As we accelerate more and more, the effective echo spacing goes down and the distortion decreases. Again, we're outrunning the distortions. There's some limits. This is with a 32-channel coil built by Boris. As we go further and further, 6, 7, 8, we start to break down, we start to pull in some defect artifacts and some noise cancellation. So there's some limit to how far we can push the parallel imaging acceleration. But as you can appreciate, between RECOS 1 and RECOS 4, we can actually eliminate a lot of this distortion at the scanner just through kind of tailoring the acquisition and taking into account the fact that longer readouts increase the distortion. Another issue that we have at 17 or higher fields is deep and dropout, again, with susceptibility regions, tissue air interfaces around frontal sinuses and the ear canals. This is sort of an exaggerated example, 6 millimeters isotropic, although, I'm sorry, 6 millimeter thick slice, although it's sort of a clinical slice thickness. One way to mitigate this, artifact is just to make the slices thinner and thinner. Because we have lower sonar, we can actually achieve smaller and smaller slice thicknesses, so 5, 4, 3. As we make the slice thinner and thinner, there's less dephasing across the slice and therefore less dropout, 2, 1. As we go to 1 millimeter thick slices, or even 0.75, which, in a lot of cases you have with SNR to cheese, you can almost eliminate this dropout. So this is another strategy for reducing some of the distortions that we see at high fields. Another issue that we need to take into account is that, beyond just the distortion, there are some blurring effects due to the long readouts in EPI that we get in both gradient echo and spin echo EPI readouts. Different forms of distortion, but what happens is, because there is a relaxation during the readout, there's a multiplicative weighting across K-space, which translates into a convolution or blurring in the image domain. So these forms of blurring in the slow encoding direction or the phase encoding direction need to be taken into account for high resolution imaging. So what's interesting is that this voxel blur in the phase encoding direction is a function of EPI duration. Here I've plotted the stretching of the voxels in the phase encoding direction as a function of the EPI readout. Now note this is beyond the sort of normal point spread function of the voxel that's due to the Fourier truncation. This is the blurring primarily due to the voxel blur in the phase encoding direction. Now, what's interesting is that this is a function of T2 star. So a general rule of thumb is that if the EPI readout duration is equal to T2 star, you get about a 4% blur of the voxel in the phase encoding direction. And the problem is that T2 star varies across the brain. It's sort of an extrinsic property, depends on the shim and on the voxel size and so forth. So in parts of the brain where there's a slightly shorter T2 star, such as in the frontal cortex, you're actually going to get more blurring as a function of EPI readout duration. And parts of the brain where the T2 star is a little bit longer, such as in visual cortex, you might get a little bit less blurring. But what this means is that you're getting a spatially varying blur across the image as a function of the local T2 star and EPI readout duration. This needs to be taken into account. What this also means is that parallel imaging, by shortening the EPI readout duration, actually also can reduce blur. Not only does it reduce the sort of geometric distortion, it can reduce blurring in the EPI images. Now, another issue that we have with some of the sort of modern gradient coils, a lot of these modern gradient coils have been designed with a little bit of gradient nonlinearity built in. This is how they achieve a little bit higher performance, like the Connectome scanner. So this gradient nonlinearity causes some geometric distortion in images. It also causes some intensity bias when there's sort of a pixel pileup. That can also cause a spatially non-uniform voxel size. Now, these first two we can correct. This third one, not so easy, but at least we can characterize it. So to give you a demonstration of what the gradient nonlinearity looks like, in our 7 Tesla, here's an EPI image, before and after gradient nonlinearity correction. You see there's actually a pretty big shift, especially in the visual cortex there. But if you zoom in, you can actually see that when we correct the image, there's some blurring induced. That's because we get some subvoxel shifts, so we have to resample the image onto our voxel grid, and it requires interpolation, and this blurs the image. So again, this is an issue which can also reduce the spatial resolution of the image. One strategy for getting around this is to, rather than resampling the EPI images themselves, what we do for our fMRI analyses using surfaces is actually deform the surfaces instead. So this is nice because it allows us to avoid the sort of unnecessary resampling of the EPI images. But the point is that, which can also not only cause a reduction in spatial resolution, we can also introduce spurious correlations in the data. So again, there's some strategies that we can investigate for avoiding this blurring and still taking into account the geometric distortion due to the gradient nonlinearity. As I mentioned, The gradient nonlinearity also affects voxel sizes. In places where the gradient is a little bit stronger than it's supposed to be significant because it's a little bit higher than linear. We actually get smaller voxels than what we intend. In places where the gradient is weaker, we get bigger voxels. So here's sort of a map. What's interesting is that this is the this is ACD4. What's funny is that you see the red region in the cerebellum. The voxels are bigger than what they're supposed to be, but in visual cortex they're smaller, which is good news for us. But the point is, this is yet another source of spatially varying resolution in the images that we need to take into account. Now, with all of these distortions and artifacts I mentioned to you, I mean, again, we do get an increase in CNR as we go to higher fields. Here's an example from Christina. This is a whole brain high-resolution 16 network, default mode, 0.75 ISO. We can see the default mode network is 16 inches square, so this is really nice. Again, really small voxels, but we have enough CNR to be able to see the nodes of this network pretty clearly. You know, also, you might imagine with such thin slices, it takes a long time to recover the entire brain. So we're using other parametric techniques such as Cowan's simultaneous multi-slice CPI with a blip cut and shift. This can enable us to achieve the high resolution of the entire brain. This is, I think, our first example. This is 1 millimeter isotropic, multiband 3, factor of 2 acceleration in plane. Here we're able to achieve whole brain 1 millimeter isotropic API, single shot in under 3 seconds. And so basically, so multiband refers to the pulses on it. So we use these multiband pulses to achieve the simultaneous multi-slice acquisition. And simultaneous multi-slices existed for 15 years or so. Multiband is one step. And the next step was the synaptic cut, which really improved the G factor to make it usable. But yeah, so we refer to multiband factor, which corresponds to how many bands we have in these slice selective pulses. Now we've pushed this a little bit further. This is some data from a couple weeks ago. I wanted to push the system as far as it go. This is, with Florian's help, this is actually Steve to that's a recon that goes in 2 points. Just one. It's 2.1. Okay, thanks. This example, I don't know if I showed this to you already, but this is multiband 4 R equals 4 in plane, so a total acceleration factor of 16. So note that there is an interaction between the multiband acceleration and the slice acceleration and in-plane acceleration. So typically, if you increase the acceleration on one, which would cutting into the performance of the level. So those what we like to think of the total acceleration factor, so the limit. So here, this is a total acceleration factor of 16 with our 32-channel coil. Again, this is really enabled by some improvements that we've made recently to the image reconstruction, notably the Steve's leak block and faster reconstruction. Just wanted to show you guys this very quickly. Okay, so with that, I'd like to move on. I've talked a little bit about resolution distortion and image acquisition with some high to 7 Tesla fMRI. Now to talk a little bit about the biological limits on resolution and see how fine scale of hemodynamic regulation may be. And we're interested in this because lately we've been working on looking at the spatial heterogeneity of specificity, looking at the tangential specificity of the bold response as a function of depth. And we've also been recently looking at intergradient specificity to see if there's any evidence for laminar level regulation of the response that we need in order to see functional differences between different cortical layers. And of course, these two characterizations are going to be needed for both columnar and laminar features of the functional architecture. But there have been some recent studies that have shown differences in bold response properties across the layers, usually showing either an earliest or greatest blood flow response or bold response at central layers. This has been seen with many different studies: granicle bold, spinicle bold, CBV using a blood pool contrast agent like Myon, CBF using ASL, and differences between these signal sources. But what's tricky about these studies is that they typically use stimuli to sort of activate the entire sort of column. You see a slight difference in the bold response in the central cortical layers. So this isn't necessarily evidence for kind of local blood flow regulation. Exactly. That's what I'm making. Yeah, exactly on the next slide. Yeah, so they don't. People have seen, for example, like CBV changes, mostly the highest in central cortical layers, but now taking into account the fact that, as I was about to mention, the vascular layers are very similar to the cell layers. We have this very high density capillary bed, as I was saying in layer 4. So the fact that people are seeing larger CBV changes may just be reflecting some uninteresting kind of vascular physiology across layers. It's not really indicative of local blood flow control that we would need in order to see functional differences between different cortical layers. And it's interesting, the vascular layers are very similar to the cell layers. I mean, we know that there's some adaptation, there's some plasticity of the vasculature. What's interesting here is another example. Here, this is showing, again, a very dense capillary bed in layer 4, but just to orient you, this isn't human. This is the calcium sulcus. This is the white matter. You actually see the density of this capillary bed actually fall very abruptly after the organ. So here's another example that the vasculature actually follows the functional architecture very closely. So it's very difficult to tease these things apart. And I think that a lot of these studies have seen differences in, say, layer 4, but as you were just saying, I mean, these could be just reflective of the sort of increased capillary density there. So we're not really sure how to interpret these studies. However, there has been some evidence for fine-scale blood flow regulation using techniques other than fMRI. We've seen earliest and greatest flow responses in middle layers using hydrogen clearance probes. People have seen peak stimulus-evoked blood flow rate using laser Doppler and audio radiography in specific layers. Actually, one of my favorites is people have demonstrated flow responses within individual glomeruli using 2-photon microscopy. And this is cool because then the olfactory body has sort of like this continuous network of capillaries. Each glomerulus is about 10 microns. And what they did, they stimulated one organ, and they saw blood flow diverted to a single glomerulus. So that's blood flow regulation at a scale of about 200 microns. So this was sort of surprising. It was really cool as 2-photon microscopy. But the question is, since all the regulation or mechanisms for blood flow regulation appear to be in the material science, that's where this muscle tissue is. How is it that there is such fine-scale blood flow regulation for capillary? There's no smooth muscle tissue on the capillary. So how can this be? Well, people have identified some mechanisms for blood flow regulation that could be at the spatial scale of capillaries. People have seen, first of all, direct neural control of vascular sphincters that feed the capillaries, which could be giving us some increased specificity. But also, intriguingly, people have seen regulation of capillary diameter through pericytes. So we don't need smooth muscle tissue. Pericytes are these kind of non-neural cells that wrap their appendages around the vessels. These need to be able to be contractile so they can regulate the vessel diameter. What's amazing is this is one of my favorite slides, and I think that this is a movie showing capillary dilation after stimulating a pericyte with an electrode. This is in preparation, test preparation. This isn't the abstract scatter plot. This is a video that you actually see red blood cells trying to move the capillary. So it's cool. There's like this the pericyte around the capillary. You see this so is kind of stopped through the capillary because the capillary diameter is restricted. But what's cool is that a few moments after this capillary is stimulated, you can see the other two pericytes subsequently downstream also being constricted. So what this means is that there's some coordination, of the pericyte constriction both upstream and downstream along this pattern. So it seems to be some mechanism for signaling between these pericytes. I think this is fascinating. That study was actually done in the slice preparation. So the issue there is that blood pressure wasn't really in vivo levels, so people weren't sure if we could see pericyte constriction in vivo. But just recently, actually, the same group reproduced these results. They were able to demonstrate pericyte dilation of capillaries in vivo. What's amazing is that they saw that the pericyte dilation actually preceded the feeding arterial dilation. So it's not like they're responding to upstream increases in signal flow. It seems that they really are able to regulate blood flow, and they estimated about 84% of cerebral blood flow could be regulated by pericytes. So this is an interesting mechanism. And again, we've also seen, in a previous study, signal propagations along endothelial cells and make up the vessel wall. So it looks like signaling can occur along blood vessels to give rise to this sort of coordinated blood flow regulation along the really small vessels. So I think all of this evidence sort of suggests that the blood flow regulation in the brain is much higher scale than was previously believed. People think that the blood flow regulation may be the scale of 2 millimeters or so, which is going to be the biological resolution and ultimately permanent. But then you function using methodology like fMRI or optical that's based on blood flow regulation. But I think that these studies have demonstrated to us that blood flow regulation is much more precise and accurate than was previously believed. And so with this, yeah, exactly. And so what's interesting too, and what I think I can show you some slides afterwards. People have been looking at neurocyclic and what they're seeing is that there is a very early response, not always a good. We do see a positive response very, very early, and the onset of that response also seems to vary with distance from the vascular. People see a very fast response from the central cortical area, with a slower response on the surface. What's actually interesting is that you actually do end up seeing more of an ASO dip at the surface because of the sort of blood flow regulation time investment. But the bottom line is it seems that the blood flow response kicks in very quickly. I just had a recent study. I think that's definitely sub-second. But the thing is, it spreads, both spatially and temporally. So I do think that, dip or not, the early response does give you more specificity. People have shown this with integrated response. The question remains, exactly how fast is it? I know that one of the boards had a recent paper showing very similar to the ECHO results that you could see capillary dilation of the seeded extracerebral calcium signal, which also calls into question whether the astrocytes really play a dominant role in blood coagulation. Even the later blood cells, which may continue 1 or 2 seconds later, but we are seeing blood dilation, like muscle dilation of the seeded astrocytes. So I think that there's a lot of evidence for very rapid, very precise blood coagulation. And I think it probably depends on where you are, what brain area. But I think that a lot of the previous thinking about spatial and temporal resolution of fMRI has been kind of revisited based on these results. And so with that, I'm just going to transition now into the next section. I'd like to talk a little bit about kind of analysis strategies for achieving high resolution fMRI. So again, we've got these small boxes here, so what can we do with them? So we know that it's possible to exploit the different spatial scales of vascular anatomy that we see in the cortex. This is a vascular corrosion cast from macaque V1. You see the large peel vessels that drain deoxygenated blood from large cortical domains. On the surface, we have the diving venules that penetrate perpendicularly into the cortex. And in the parenchyma in the center of the cortex, you have this sort of dense limited oriented capillary bed. So the idea is that if we can take our small voxels, we can exploit this sort of regularity or this hierarchy of vascular organization to perform what we call a sort of an anatomically informed sampling. So the idea is that if we consider our small voxels that are really here in parenchyma near to the capillary bed, presumably the spatial coupling between the blood flow responses and the relativity of the tightest, we can potentially achieve higher resolution. Whereas if we can sort of avoid voxels that are sitting near the peel veins, which again are draining blood from large domains, we can sort of avoid those voxels. We could potentially remove some of the sources of spatial inaccuracy of our measurements. So in order to test this idea out, we employed the concept of retinotopy. So this is a property that's shared by many visual systems. It's the property in which nearby neurons possess receptive fields in a nearby visual field. So the idea is that every neuron in the visual cortex is looking at one spotlight in the visual field. If anything goes into that spotlight, the neuron fires. And what's interesting is that nearby neurons in the visual cortex have nearby spotlights. So if you kind of extrapolate this, what you see is that there's a topographic map of the visual field laid out into the cortical surface as part of a action tactical tool. So the idea is that if the subject is looking at a particular scene, if you could image while they're looking at that, the pattern of neural activity, it would resemble the scene at the retina. So again, one interesting feature of this mapping is that there's a variable magnification. There's actually more neurons devoted to representing the center of the visual field and then to the periphery. And this is reflected in the mapping. You see here in this cartoon, the representation of open space, which is in the center of the visual field, is expanded relative to the periphery of the visual field, which is represented in the small cerebral cortex. Also note that the receptive field centers that give rise to this topographic mapping are organized in a columnar fashion. So we wanted to exploit this retinotopy in order to test this idea. In order to do this, we developed a novel cortical depth analysis. We did was using our right surfaces, we identified the right surface as a free shifter, and then evolved that surface out towards the field surface following local image intensity gradients and saving intermediate surfaces at different cortical depths. So in this case, we generated the family of surfaces, the two boundary surfaces, the interior exterior boundary of the cortical gray matter, plus these sort of non-intermediate surfaces. And also in the upper layers of these surfaces, so the cross sections of these surfaces overlaid onto our grains. So again, what we did in this analysis is simply identify DPI voxels that intersected each of these surfaces. So in this analysis, we're actually generating one surface model per depth. And this enables us to perform sort of a laminar or depth analysis for large expanses of the cortex, restricted to looking at what's locally flat patch of tissue, as was previously performed for these laminar analyses. So as I mentioned, we want to exploit retinotopy, so we designed a resolution stimulus that used a retinotopic model to impose a desired activation pattern on the V1 surface. So for example, if we wanted to elicit a pattern of neural activation in the surface of the red, all we would do is calculate the visual stimulus that we would have to project in order to elicit this sort of pattern of activation. We can do this using a simple kind of mathematical transform. So again, we're sort of pre-distorting the visual stimulus. Here's what it looks like. Here we have our M stimulus. So note, the retina kind of inverts the visual image. So we kind of flipped our M upside down. We presented one on the left visual field, one on the right visual field. So here's our condition A. It's a noise-filled M on a gray background. We contrasted this with a gray-filled M on a noise background. In order to drive the neurons in V1 crazy, we had this spatially scaled noise pattern that kind of flickered at 8 Hertz. We have to use a fixation task to minimize eye movement. Imagine if the subject's moving their eyes during this experiment, it's going to blur out the activation pattern on the surface. We really needed to make sure that the subjects were keeping accurate fixation. Actually, we limited these scans just to 5 minutes to make sure that the subjects didn't get fatigued and move their eyes all the way around. So here's what the activation looks like, in the folded representation within a single slice. Again, what we did was we identified fMRI voxels that intersected our family of intermediate surfaces, and we just sampled the z-statistic of the activation as a function of cortical depth. Here's what the pattern looks like on the cortical surface representation. You guys are familiar with this. It's really tough to see the pattern in the folded representation. The arms with the cortical surface and the folded representation, you can much more clearly see the spatial pattern of activation. Larry always likes to see the, well, no, of course, that's the point of this experiment, is the spatial resolution, but also unthresholded kind of data. This is just the same thing shown in MATLAB. It's pretty clear. But again, the point of this experiment was to investigate the depth dependence, spatial accuracy, to test this idea of this vascular, whether we can exploit the vascular regularity. So when we sampled this pattern near to the white matter surface, the spatial fidelity of the pattern is actually quite good. You can see the PBM pretty clearly. But as you progressively sample closer and closer to those large PL vessels of the cortical surface, the spatial fidelity of the pattern breaks down systematically. And I think in an interesting way, so this is one of my favorite artifacts, right here. It looks like maybe there's like some PL vessel that's sort of running across the background of the pattern. So what's interesting is that we're seeing the spatial breakdown is interesting. First of all, it degrades as we sample closer to the PL vessels, and maybe not surprising. But note that this resolution is not really well characterized by some isotropic Gaussian zero-made point spread function. And it's also not as if the pattern of the measuring to the PL surface is simply a blurred pattern of what we're seeing at the white matter surface. The pattern breaks down in a much more consistent way. I think of obviously because small voxels are very much more sensitive to local details of the vascular anatomy. But also note that while the resolution breaks down as we sample closer to the surface, the z-statistics actually even higher, which I think larger signal changes, which is to be expected. So we wanted to plot this. So here we're looking at the percent signal changes near to the white matter surface and plotting it as a function of depth all the way up to the PL surface. So we see about a 1.5% signal change near the white matter surface, but about twice that near the PL surface. Now, again, that's not surprising because these large things are draining lots of blood, so we're actually getting higher and higher percent signal changes near to the PL surface. What this also means is that there's a trade-off here between sensitivity and specificity. It's kind of depressing that we get the most sensitivity near the PL surface exactly where the accuracy is the lowest, but this is also kind of nice. It represents a knob we can turn. If we need more specificity, say we'll need the white matter surface. If we need more sensitivity, we can go to the PL surface for these columnar activation patterns. We also want to look at the spatial variability of the percent signal change. So this is kind of the spatial variability of the percent signal change. What this is reflecting is that when we sample near to the white matter surface, we get pretty much the same, like 1.5% signal change. It doesn't really vary very much. But when we sample near the PL surface, we see both big percent signal changes and small percent signal changes. And why is that? Well, we think that it's reflecting the spatial heterogeneity of vessel sizes near the PL surface. This is a photograph of the cortical surface. See the vascular network. So we think that this is reflecting the broad distribution of vessel sizes. We have both big vessels and small vessels near the PL surface. So depending on the voxel, we may be seeing either big percent signal changes or small signal changes. So again, we think the spatial variability of the fluctuation amplitudes just reflects the spatial variability of the vessel sizes. So in summary, so we see a largest percent signal change exactly where the foot's going to be the lowest. So there's some trade-off here. And again, we see the spatial variability of the percent signal change and the pattern also increases as we sample closer to the PL surface. Now, it's tough to talk about high-resolution 7T fMRI without some mention of spinnacle EPI. So as many of you know, at higher fields, we really get no intravascular signal because most of the acute cells are really short. So all of the signal change we see in bold is extravascular. And we know that from simulations, that we know that the spinnacle is preferably sensitive extravascular bold signal changes around small vessels. So it's been kind of promoted as a technique that can give us higher specificity because it's only sensitive to signal changes around the smallest vessels. So I wanted to test this out. We performed, this is just one subject. This is a little bit longer scan. We did a gradient echo and spin echo M. We didn't really see a big difference in the spatial spread. The hypothesis here was that if spin echo was only sensitive to small vessels, extravascular bold around small vessels, you would expect the spatial spread to be sort of tighter in the spin echo, and we wouldn't expect it to change very much as we sample closer to the surface. This is sort of one subject, but you can see that I think the spatial spread is comparable. Now, note there's some issues here. The spin echo signal is a lot lower, and it's hard to kind of separate out kind of resolution effects from SNL effects. Maybe we need to kind of do like a more fair comparison. That's a little bit tricky. Like, how do we do this? And we can maybe cut down on the gradient echo, or I think it's a little bit tricky. Also note that SAR limits coverage. This is funny. So I ran into a SAR limit on this experiment, so I had to cut down the number of slices. So actually, accidentally cut off a little bit of the signal mode. This is another kind of practical issue with using spin echo API. And so again, I think we're going to need some SNR matched comparison. But what we learned from this experiment is that it's actually kind of tricky to actually get the benefit of the spin-up API, which almost kind of simulations. Our readouts here are actually kind of wrong, and we're pulling in some potentially T2 prime or T2 small effects. And that's because we're only really getting that pure T2 spinnaker weighting at the echo in the center of K-space. And this phenomenon was actually nicely demonstrated by Nikos Logothetis' lab. So this is macaque visual cortex. So he first started off, this is a kind of a depth analysis. They measured the sensitive change of the field surface on the molecular surface. And he looked at the gradient echo bold, and he saw that, as expected, with a kind of simple visual stimulus, that peak gradient echo bold signal change along the cortical surface, on the clear vessels, very similar to us. But then he performed a spin echo API, again at 4.7 Tesla, and again he found that the peak signal change is also again to the clear vessels, these large vessels. So why is that? Again, spin echo is supposed to be only sensitive to small vessels, although he's seeing a peak signal change on the large vessels. Although there's kind of a secondary peak, in a Planck way we'd expect it. So then he realized that there might be some, because of these long API readouts or some T2 prime weightings, what he did was he reduced the readout by increasing the number of shots. So from a 4-shot spinnaker API, the 8-shot spinnaker API has halved the API readout, and less T2 prime effects. All of a sudden, you see that there's a peak spinnaker bold seen in the supracortical layers in the site of the smallest vessels. So we're seeing that the spinnaker signal is shifting towards the smaller vessels. As he went even one step further, 16-shot spinnaker API with a very short readout, so it's much more kind of approximating the effects himself in simulations. You're seeing that the peak bolts that is occurring in the supracortical layers of the site and the smallest vessels. So what we're seeing here is that, in our experiments, we sort of here in the middle, we actually do have long readouts in the spinnaker API. Spinnaker API is difficult to use in fact, just because it requires super short readouts, which are assisted into a segment of the multi-shot API, which in my hands is actually pretty challenging to pull off. So the point here is that I wanted to address the spinnaker issue, but the point is that it's really challenging to get this to work in practice. Okay, and with that, I'd like to move on. I'd like to talk a little bit about some novel acquisition strategies. These are a couple of things that we've been working on in the lab that I thought that you guys might be interested in. So the first issue that we've been kind of tackling, especially for our high-resolution fMRI, which I told you we were really relying a lot on heavy-duty, lots of parallel imaging. We're seeing some effects of motion during the ACS. So this is sort of a typical time series. You see this. This is a time series as SNR. We're seeing to see over and over again. This is sort of striped pattern. We see discontinuous SNR across our slices whenever doing kind of high acceleration factors. Now, what we realized was that this is only occurring when we're using auto-calibration data that is multi-shot. So if you actually do the exact same data and calibrated it with a single-shot ACS acquisition, this discontinuous SNR just goes away. You also get a pretty big increase in SNR. And we were really puzzled by this at first. Why is this? We saw this both in the time series SNR and in image SNR. So it's not just a triple stability thing, it really is something to do with power management. I wanted to dig into this. We realized that this discontinuous SNR across slices, can be a real problem for any activation, studies in fMRI, of course DTI as well, because most of our fMRI studies are based, solving a detection problem. This is a DSCS box. So we just kind of put this out. We looked into it. It looks like that this is due to some effects of motion or instability in the multi-shot ACS data that we require for graphic reconstruction. So any kind of subject motion, some patients that are prone to motion and you guys are interested in. Also, we're seeing that dynamic B0 changes due to respiration can also cause this. So the solution that we proposed is to just reorder the acquisition of these segments to minimize the time interval between segments in each slice to make these ACS acquisition less vulnerable. I just want to explain that really briefly. So in conventional kind of multi-slice API, what we do for our acquisition of the auto-calibration data is we use like multi-shot, and conventional multi-shot works like this. So say we have 3 shots. First we acquire segment A of slice 1, then segment A of slice 2, and segment A of slice 3, all the way down. And then after we've acquired all of the slices, we go back to the beginning and acquire segment B of slice 1, segment B of slice 2, and so on. So what this causes is a pretty long time interval between the segments within any individual slice. This is nice because it allows to, on recovery, we can kind of maximize the signal in a given slice. But this long time interval between the segments really increases our vulnerability to motion. So our proposed reordering scheme, known as FLEET, what it does is it acquires, just sort of reorders the acquisition. We acquire segment A of slice 1, then segment B of slice 1, then segment C of slice 1. and so on. So we've actually minimized the time interval between the segments. This makes this gives us a much less T1 recovery, so we're taking a little bit of hit in SNR of the ACS data, but we're much more robust to motion and dynamic phase changes. We call this FLEET. This is actually an old idea by Sir Peter Mansfield. It stands for fast, low-angle excitation uppercutting technique. It's kind of a hybrid between EPI and flash. Actually, we came up with this before there was multi-slice EPI, so the only way to do segmented. And so the idea is that in order to balance the magnetization across the shots, you use a tailor, your flip angles. So based on your TR and T1, you can calculate the flip angle progression in order to give you equal magnetization across the segments. This is known as a FLEET, a variable flip angle. But also, because we have multiple T1s present in the system, it's kind of tough to kind of come up with one flip angle progression that works for the entire brain. So it's also possible just to use a bunch of low flip angles, like say 20-20-20, which gives us equal magnetization across the shots. And this is the technique that we typically use for our ACS. So again, the idea is to just replace conventional multi-shot EPI with a FLEET acquisition. And this is nice. All you're doing is you're changing the ACS data, not changing any of the optimal acquisition, not changing the image reconstruction. You use a conventional graphic training and reconstruction. And we've compared it with a sort of a newly implemented Flash ACS. So here's a quick example. When we use either the Flash or the FLEET ACS, we eliminate the discontinuous SNR axis. Again, because we're removing the vulnerability in the conventional segmented EPI acquisition for the ACS, and this is giving us, less phase misalignment across the segments and letting properly extract. We're also seeing sort of across the board that the product ACS tends to have much lower SNR than the FLEET ACS. We see about a 20% improvement in TSNR just by using the FLEET. Now, this is including all slices. I think that in the bad slices, even more the relative boost, so we're using the FLEET ACS. We compared this to a Flash readout. The problem with Flash is that it's not epispacing matched to the accelerated data. So whenever there's zero distortions, the Flash ACS data doesn't match geometrically the accelerated data. So we see a much lower ghosting when we're using a FLEET readout compared to the Flash. And here's a quick example of the motion and sensitivity. Here's a movie. It's taking a little while to get going. But you can see we built this mechanical phantom. It's an anthropomorphic head phantom. This is actually a really helpful device. Putting the scanner in a conventional ACS conventional API. You can see the phantom's moving throughout the entire scan. You can see a lot of the scanners and artifacts because it's moving during the multi-shot conventional multi-shot ACS acquisition, so that's bad. When we use the FLEET acquisition, the phantom's still moving, of course, but all of these areas are artifacts of it. Because we're removing the vulnerability of the multi-shot ACS acquisition to motion. And just to quantify this effect, again, this is the same data, TSNR map. We see that the FLEET and the conventional acquisition has purchased in SNR a little bit higher, but of course, when in the presence of motion, the SNR plummets using the conventional acquisition, whereas the FLEET is able to maintain high SNR. And again, what we saw was also that's a good question. So we have investigated this in the context of, I'm going to show in a couple of slides, we integrated this also with our SOS other collaborations there. It does seem to have a little bit of an effect. I mean, what we see is that and any kind of motion is going to affect the training with the kind of implant acceleration, both the rotation and also in this slide, it's a little bit of also respiration. We've also seen, I think I got one slide showing these aggregates, during the ACS acquisition from parasite producers. I think that I do think that we're seeing less of an issue with rotational, in-plane rotation than the pattern. It's definitely just a difference. But yeah, thanks for that. I still haven't looked at it systematically, that's sort of anecdotal, but I think we are seeing this. But just to kind of characterize the effect of breathing, so again, when you breathe, your chest fills with nothing air, and it causes visual change in the head. So here, again, sort of typical free breathing acquisition, we see this discontinuous SNR that I've been complaining about. If we use the FLEET, we actually get rid of this discontinuous SNR, as I showed you before. We also get sort of across the board increase in TSNR. But when we ask the subjects to hold their breath, yes, which is about 20 seconds, I'm actually not very happy. Again, that's not we're eliminating the sort of dynamic visual changes that cause space misalignment across the segments. This enables rapid to happen and edit this discontinuous SNR issue. And again, if you run FLEET during a breath hold, isn't affected, of course. So the idea is you can either use FLEET, or you can ask the subjects to hold their breath during the ACS acquisition. just to show you that, there it is. Yeah, and just to make the point, this issue isn't about, signal intensity differences across slices. It's not like a slice profile issue. There is a instability or time series instability issue. So this, here I'm showing you this the time series standard deviation of these data. So you can see is that in normal free breathing case, we're seeing that the time series standard deviation is discontinuous across the slices, whereas in the axis of time, so it's not a signal intensity issue, it's a signal variability issue across time. And what's funny is that the first time we did this, we were surprised to see that, just even on a scanner, we just did a standard deviation log, and we see very clear that charts quite a bit across slices. Now, what's nice about the fleet ACS, it's also like pretty short. Just to show you real quick, the fleet ACS has advantages over Flash. One of them is that it's much shorter acquisition. So in this case, it's about 1/3 the duration of the Flash ACS acquisition. So again, the fleet ACS removes this SNR discontinuity, which is caused by motion or respiration, increases the TSNR, and reduces ghosting in the presence of B0 and homogeneity, which is especially important for high field. As I mentioned, I'm just going to show you real quick. I mean, I think this is kind of obvious. We've applied this to our SMS. We've sort of reordered the acquisition of our SMS calibration in order to make it more motion insensitive. The idea is that, the conventional SMS, say you're doing an acceleration factor of 3, you would acquire, say your 3 slices simultaneously and tile the entire brain. The way it would typically acquire the reference data, is to simply just do it sequentially, and of course this causes a big time gap between the slices that are clocked in accelerated version. So it was kind of a simple idea, but all we did was sort of reorder the acquisition of the slices to make the calibration for the SMS data a bit more robust to motion. So a simple idea. This is the one example I was mentioning to you. Again, this is during free breathing. This is one we've incorporated. This is both, this is no in plane acceleration, MB factor of 6. We're seeing, pretty good image quality. Wait, what here? Oh yeah, I'm sorry. I got confused here. I just put these in this morning. So this is acquisition using a conventional SMS that you see pretty good SNR, but once we use the SMS fleet, we actually get a pretty nice increase in SNR. During free breathing, also these are the eyeball artifacts as mentioned to you. We're seeing these artifacts here in the occipital lobe, and we use the fleet SMS, these artifacts are removed. We've also incorporated this into our 7T data. You can see again quite clearly in the presence of motion, we get some pretty strong ghosting artifacts. We use the conventional acquisition, which are removed when we use the SMS fleet. Okay, so as I mentioned, I think that the benefits of this motion-sensitive ACS is that, any motion during this 1/22nd vulnerable period can just correct the entire motion. It's this really critical moment where, you really need the most accurate data as possible. Well, nowadays, since we're pushing the recons further and further, the reconstruction times are really lagging. So typically what we used to do back in the day is, if you saw a bad scan, we would just stop and restart because, if the subject was coughing during the ACS, you can just restart the scan. But nowadays, since the recon is usually lagging by many minutes, it's tough to do that. You don't know that the scan is corrupted until the subject's out of the scanner. Also, it enables higher acceleration factors. This problem gets worse and worse as we go to higher and higher acceleration. I think that's all I'd like to say about that. So I'd also like to talk to you about another couple of cool projects going on. The world got these slides we've been looking about Jason Stockman. He's been looking at B0 shimming, looking at spherical harmonic shimming compared to arrays of local shim coils. This is kind of a typical B0 map after sort of standard second order spherical harmonic shimming. So Jason's been simulating the effects of using multi-coil shims. These are arrays of local shim coils tiled around the head in the same geometry as our receive coils. We can see that we can eliminate, especially around the frontal sinuses with 32 of these local shim coils, we can eliminate a lot of the B0 inhomogeneity in the brain. So what Jason has done with Larry is they've realized that they can actually use the same conductor used for NAV coils for local shim coils. Because the shims are sort of DC and RF and RF, they can actually serve a semiconductor. So what he's done is he's taken an existing 32-channel coil and added to it, just by a couple of shims, a couple of chokes, and some guide wires. He's able to actually use the same conductors for local shimming, which is pretty cool. So, and it's nice also because apparently, since there's so slow inductance on these coils, you can switch the current really quickly. So I think he said that for that 10, 20, 30 microsecond switching time. So this enables dynamic shimming, and also because the coils are so close to the head, the current requirements are very low because the magnetic fields are so close to the tissue. So here's an example of his first in vivo shim results. Is a 3T, working on a 7T version now. So here you see the kind of second order, the results of kind of typical kind of product second order shimming, the predicted B0 maps using a multi-coil shim array, and his measurement in vivo. You can see that with just 10 amps of current total, he can reduce the B0 homogeneity by about 50%. Pretty exciting. He's also applied it to EPI. Here we're looking at, on the left, the EPI images using a second order shim, a typical second order shim, this is in the one, EPI is in the multi-coil shim. So this is cool because, again, he's not taking up any more real estate for the shim coils. It's using the exact same conductors as the RF array. So I think this is really cool, very exciting technology. What's nice is that, as I mentioned to you guys before, he's removing the distortion, distributed by accelerating, there's some limits to how far we can accelerate. So if we can eliminate some of the B0 distortions through the shim coils, we can take some of the burden off of our parallel imaging acceleration and achieve high resolution EPI with distortion mitigation. Another kind of project I wanted to mention to you guys, this is in collaboration with Andre Vanderpoel. We've been looking at high resolution MP ranges. So just like the EPI data that I showed you guys before, during the MP range, we do an inversion, we do that many different lines. During the MP range readout, there's some T1 recovery. This causes a multiplicative widening of free space, which causes again a convolution or blurring of the image data. And this blurring is, of course, a function of the T1 tissue process, which are the recovery for the wetland and suicide. So this results in kind of tissue-dependent, T1-dependent blurring function, which is also a function of the readout of the MP range. So we thought, to try to reduce this readout by employing parallel imaging, we thought that maybe we can accelerate during the inversion recovery. People thought this is crazy, you can accelerate during the inversion recovery, but we do the same thing during the T2 to start with the ATI, so we have to try it. So the idea here is to reduce the readout during the inversion recovery by using parallel imaging in the inner loop. So we're calling this inner loop grappa. This reduces the readout, and this can also substantially reduce the blurring due to the T1 recovery during these readouts. Also, it gives us a more kind of representative inversion time. Typically, the inversion time is the center of the readout, and that's not really representative of this readout. So the nice thing is that we get a better T1. What we can do now is, now that we're accelerating these readouts, we can actually incorporate multiple readouts per inversion recovery. Each readout is short, so each readout has very little blur, but we can tack in multiple readouts, each of which has its own TI. So during one readout, we can actually get multiple contrasts. And this is nice because not only is each contrast going to have reduced blurring and reduced distortion, but we can take all these readouts together, each of which have different TI, and fit T1, the quantitative T1 maps. This is sort of analogous to Andre's multi-echo EPI, where he increased the readout direction, increased the bandwidth in order to make the readout shorter, to reduce the distortion in the readout direction. And he enabled this enabled him to achieve multiple echo times. So here we're extending this this idea. We have a single readout that has multiple echo times, multiple inversions. We can set up the TVs to give us multiple contrast with which to style. We can use multiple inversions to fit T1. So it's going to tile this parameter space. We've played with a 3 echo, 3 inversion, 4 echo, 1 inversion, 1 echo, 4 inversion. Here's one example. This is a single 6-minute acquisition, 900 microns isotropic, 4 echoes, 3 inversions. Here you see the echoes across the horizontal axis, the inversions across the vertical axis. What's nice is that you can combine all of this data in multiple ways. You can just do a sum of squares combination to pull back more SMR, so the only signal losses are due to the package feedback. What's also nice is because each of these readouts kind of has its own alpha tone. The phase evolution across each of these individual readouts is the same, so you can actually combine the data as complex values. So there's really the only signal loss is due to grappa G factor. But as I mentioned, because we have multiple contrasts, we can actually fit parameter estimates. Here we're showing both a T1 map and a PD map from our gold standard on the left, and the so-called multi-echo, multi-inversion MP range. This is you can think of this as a generalization of the MP2 range acquisition, so we've been calling it MPX range. You can accelerate by a factor of 3, 4, 5, and as you accelerate to higher and higher factors, you can include more and more TIs. So here's an example. We just combined using RMS. This is the volume bias correction. Again, 9 microns isotropic. And of course, we pump this through FreeSurfer. So again, I think this is an important technique, not only because it gives us more contrast, which we can do quantitative ML, but it also reduces the blurring. One acquisition, actually, this is our first application of this sort of inner loop grappa accelerating during the partition recording. We actually did this, I think, last year at HBR. This is a record 290 micron isotropic, adults, in vivo testing. Of course, we only could do this with Dylan's perspective motion correction. But again, the problem is that as the readouts in the range get higher and higher, get longer and longer, and we achieve these small voxels, we're getting more and more blurred. So a lot of people now are moving towards high resolution or small voxel MPH, but I think that there's so much blurring in the partition encoding direction that they don't have the voxel sizes that they think. So we think that this inner loop grappa technique can help us to achieve very small voxels, true, honest, small voxel acquisition of range. The point of this study was actually to sort of validate our synthesis consensus. It's nice is that so the red lines correspond to the 1 millimeter kind of empty range, FreeSurfer recon, and the blue surfaces correspond to a FreeSurfer recon from this 290 micron beta. What's nice is that actually the surfaces agree pretty well. We were kind of encouraged that the FreeSurfer reconstruction from the 1 millimeter data was as accurate as it was. But we do see in a couple of places, we do see that there's some disagreement. We do see that maybe some higher resolution empty ranges could improve the accuracy of the FreeSurfer recon.
Area which is thinner and brighter in T1, so you have less apparent contrast. You think it's actually better when you use multiple.
Absolutely, that's the part of the difference. I think that another nice thing about the multi-inversion that is to fit T1. What's funny too is that I'd like to show you. We tried doing some recons after the T1 map, because of exactly the point you mentioned. Actually, T1 is shorter than the visual cortex. There's less. Yeah, exactly. So what's funny is that even with a quantitative T1 map, true durability of T1 effects. But the point is that we think that smaller voxels can help. Actually, what's funny about this is that our main goal here was to eliminate the errors in the surface reconstruction to go down. But what's funny is that even with 390 microns, we're still getting direct contamination. I mean, some of the standards to do it. But at least sort of giving us some encouragement data for the very light interface. I think this data has been really useful so far. So the point is that this wouldn't have been possible without the inner loop grappa because the readouts in the partition direction was so long that the image would be completely blurred in that direction. Okay, so I'm going to skip ahead a little bit. Okay. So another idea that we've been playing with is high-resolution T1 mapping using API. Again, our API quality is getting so good nowadays, in fact, that we're using T1 mapping. The areas that we significantly developed is quite an old idea. It's close enough to look at. All we do is we do an inversion. We read out all of our API slices, because each slice is a different API, and repeat it, do the inversion again, we get all the slices, but we create the order of the slices. If you do this enough times, enough inversions, enough permutations, each slice gets each TI. So the huge images actually come in on the scan. So in this case, we did 24 contrasts. This is 1 millimeter isotropic single shot API. 120 slices, that's the limit. We were able to achieve all of these contrasts, 24 contrasts, in just less than 3 minutes. So what we can do with this data is we can actually fit T1 recovery to T1 voxel. So this is the values across all of these 24 contrasts, 24 voxel. You can actually fit T1. Actually, we're doing this not with a parametric closed form model. We're doing it with kind of a block sim. This is now called MR fingerprinting. But the point is that we can use this to derive T1 maps. So here's an example. So kind of a residual is we call it S naught, and then it's rho plus T star. This is a residual. We're going to comment a T1 map from this data, with which we can synthesize an image, an API image with MP range like contrast, which is nice because it has very little T2 star contrast within it, and because it's basically quantitative T1, it's less vulnerable to any kind of bias field. And of course, we can take this data with a little bit of work and pump it through FreeSurfer. So here are some examples, the surface recons, and the subcortical segmentations. So this is nice because here we have surfaces generated from FreeSurfer directly on API data that's distortion matched to our movement. The idea here is that we're not going to use this for morphometry, and still every range is going to have a lot better geometric, accuracy. But for fMRI studies, where we want our surface models to do fMRI analysis, we want the surface models to be as matched to the bowl data as possible. So the idea here is that we can generate surfaces within the API data so that they're perfectly distortion matched to the fMRI. And we've been using these data not only for cortical studies, but also for some subcortical. We've been combining. Again, since our API quality, we put a lot of effort into it. We're actually able to achieve full API, QA API, efficient API. We're not sure what we're actually doing some susceptibility. We're not using API, using an asymmetric spin echo. So all of these are just completely distortion matched, and we can therefore combine all these different contrasts for a multimodal API exam. One of our first studies was looking at the brainstem. We're actually looking at assistant data at 7,000. This is a topic. We were able to see an individual components of analysis, those that correspond to the nuclei in the thalamus, which correspond quite closely to the FA map shown over on the right. What's nice is that we're seeing very high reproducibility across subjects. These are 12 of our subjects. We're actually seeing this one example area of VTA. We're seeing very high consistency across individuals. But what's nice is that this indicates sort of what it was mentioned before, and that is the potential for Tesla to be able to perform single subject imaging, which I think is quite important. We tried one continuous pain study in the cunate nucleus. Actually, also across 12 subjects, we're actually able to see. So the cunate is first relay body that relays sensory information to the body. And the idea here is that we're hoping to apply this to chronic pain subjects again. The fact is we can see this one nucleus in single subjects. And I think this is really single subject analysis. So with that, I think I'll just wrap up. So as I mentioned, 7T offers increased contrast-to-noise ratio needed for small voxels, although it poses some challenges to spatial accuracy, and these challenges, a lot of these distortions and artifacts can be mitigated in part by acquisition strategies. We've also seen that the vascular anatomy and physiology place some limits on biological resolution of fMRI, but there's both regularity and fine-scale regulation of the vasculature that we can exploit to achieve high resolution. This anatomically informed sampling that I showed you gives us a way to merge our small voxels that we can now achieve with our API with some understanding of the vascular anatomy or physiology to, again, yield high spatial accuracy. And finally, I mentioned a couple of techniques that we've been developing with the goal of further increasing our accuracy. So with that, I'd like to thank you guys for your attention. I'd like to thank my slide contributors and my colleagues, and I'm happy to take any questions. Actually, so this is at 17, so we're actually using this 80 data pulse. So I can use a pulsar pulse die, and CID is where it's an enrichment network. And it's not a blocker because each slice gets one alpha. Yes, so the alpha is something like that. It's but again, the hope is that we try to bunch of different alphas. So we're using 90s hoops to 2 noise language. The hope is that a lot of these factors will fall out and the results.
In typically the T1s and T2s are so much smaller, especially at the techniques will work, or if you need a more rapid state, keep the curve.
That's interesting. That's interesting. The T1s are longer. I mean, I think that actually a little more flexibility for a lot of these underside methods. Because one of the issues is that we need to sample quickly enough before all of the T1s are converged. So actually, all of the T1 might be enough for just but it seems like a first blush it's also true that once you look at these different populations, all of the parameters of the atmosphere are changed also, so it's probably worth taking a look at the whole thing. I think that you might not need as many partitions, for example, so you can accelerate a bit more of that. So we get to look at the whole problem, but I think that a lot of the T1 is not necessary. So I think the biggest issue that to exploit, to let the tissues differentiate, you might need to expand the longer, but it's over 2 hours, for example. So it's going to prolong, again, we have less partitions to balance out.
I think you have a different disease for something that needs factor. The normal one and the abnormal one is the range that you want to do is much bigger.
Well, that's an important point, and it's also true that when you're first setting up these protocols, we're trying to figure out how to optimize for 351 to have a set up version times for 351, but even when it almost moves, a lot of it will be. It's more across the brain. And so we actually have a pretty long, we have a pretty long list of TIs. We're not even sure that you can cover, so I think that, for example, in the US stuff, I think our TIs are enormously CSL really about 2 minutes. So we have really long range. I mean, I want to say for 1 to 1 years old. I think the shortest TI was about 4 milliseconds. I think that girl about 7 seconds. So I really make sure that he's getting everything. And what's nice is that, for the T1 stuff, also because we have 120 slices, it takes a while. We haven't put SMS in that, but it takes a long time to get all the slices. So we're automatically sort of forced to have kind of a long repetition time. So kind of, some of it will get this nice wide range of TIs. I think that, I think it's pretty long. With a good, really repetition time there, the time between the boost, which is like 7 seconds. For those slices. So 16. Oh, yeah, That's interesting. I guess it depends on the disease, of course, and I guess it's possible. I mean, I think that, they have towards several counting these techniques to reduce the neurovascular impact to patients. The main issue is just that you don't have a proper negative map. So sometimes you get false negatives that are because simply because of the issue. It's like a pathological tissues. But I can say that I mean, obviously, once the system becomes unknown, obviously, characters in terms of the clear vessels. Are you asking for the clear vessels to more? Right, but that back will go all the way down to that as well. It's true that we haven't really looked at how these ideas would be affected by different pathological conditions. And as I said, we don't look at it. We don't look at it like this magnetic therapy, or look at it really reduced the response with really high. But again, that might affect, since that's more on the material side, that might affect, that one could, for example, might affect small vessels and large vessels. So that's an interesting point. Some have a kind of I mean, I think it's one possibility. That's a good question, right? So, and one of the things that I kind of skipped over, I mean, maybe I'll just show it real quick, just as a backdrop on saying, I mean, so we have been trying to do some angiography at the moment, and it's tricky because, I mean, so first of all, with this, to start, what's nice is that we're getting increased venous contrast because it's more susceptibility with that. But what's tricky though is you can see, it's kind of tough to see the keel vessels because it's kind of a black type technique, and a lot of times you don't really see, there's no signal to subtract from on the surface. So that's what tricky. Also, as you know, this is kind of an anisotropic effect. You get more effects to the panel, these are the perpendicular. So this has been tricky. I was kind of joking about doing like MRV with TSE or something like that, where you get more signal in the background. But this has been tricky. We've also been looking at the flight, which now says that because the T1s get more from blood, it's actually you get better kind of temporal contrast, etc. This is non-contrast MRA. With the problem with these data is just that we actually get some signal from stationary tissue because they're not going to use special transfer. So the point is that we can try to recover these data into LSMR analysis. And the problem with both of these methods is there's a lot of false negatives. And if you don't see a vessel there, it doesn't mean you're useful. I think for a lot of people, have them turn out like APIs themselves, and turn out the APIs themselves, and kind of see like a signal board and know what's going on. I try things like under Thomas looking up to, like just looking at, like making a plot of the bold variability on the surface, and just projecting it onto the surface, from the boxes on the keel surface, projecting it onto a part of our surface model, and seeing if this looks like, the last one. And it did. I don't know why, and maybe we need more averages. Yeah, and also with the trick is that another thing we're looking at is trying to measure physiology. So if we can measure cardiac respiratory CO2, we do know that there are more sources of physiological noise at the surface. The problem is most of our measures of that physiological noise are systemic, like the bellows or pulse oxy. And we're starting to see that these systemic signals, after they propagate through the brain, they kind of they're filtered a little bit to feel differently across the brain. Sometimes we're seeing places where the signals are interacting in some weird ways. And but you're right, I'd love to dig into this more. And again, we have been kind of hammering this stuff. I feel like it's not at the stage yet where, we really have confidence in it. And most of the time, actually, what's nice about this scenario is that we treated here, because, typically we kind of sat out the sagittal sinus to get just the arteries. That's it. The solar there is through the roof. So at 17, we actually take out that sacrament. So actually, we're getting kind of inflow effects on the external side and the inner side, which is, feature anecdote, and so I think that obviously a lot of times because we're too spot, one of the device on the other side, but we are getting involved in the chip, because the top flag is that it's only measuring like blood that's flowing into your slab, so you really need to pick your slab very carefully. But that completely wipes out the issue. I mean, we haven't played with some confrontations, especially for the NRA, but again, so a lot of these tend to really have like a pretty big effect on the surface. But this is also big, and it can wipe out the first the top half of the cortex. That's really refine that. So the collection of images. And looks like you're correct. Yeah, there's some stretching effects. Yeah, it's funny. And it's, yeah, it's a good question. And there's a couple of tricks that we can play as we found this. Tricks we can play in order to ensure that a lot of these questions, sometimes the overcorrect. I talk about the shoe example. Yeah, the Shum example. I mean, don't get me wrong. That was his first attempt. I think I saw what you saw, which is that it looks like maybe he's yeah, but something was better. Yeah, but I think that the problem with these local show clothes is that they have so many degrees of freedom. I think one other thing which is because all of the distortion applies in the direction of the vision, what we can do is use actually flip projection. So all the distortion is not going in the opposite direction. It's nice validation because if you apply the distortion correction to both of these images, in theory, if you're correct, there's that's one kind of validation that we can play. Also, we can we can acquire different types of DPI data. Even acquire like a segment to like a shot that has a lot of distortion. And just sort of kind of cross validate. I'm not sure that's the right word, but sort of validate these distortions by applying them progressively to. Yeah, that's a good point. In general, this distortion correction is tough business. I mean, just thinking of feedback and doing distortion correction, oftentimes make things worse. And distortion correction is tough, which is why I really like power imaging as a means to sort of eliminate the distortion, rather than correcting acquire images that are relatively distorted through. I think that's much safer. So yeah, I think this is again as very first exercise. I agree with you that I think that could be refined, but I think it's a promising. That's nice.
So,
Sure. Do I just stop?
yeah,